Hey guys, welcome back to STEM in Style. My name is Vanessa and this is Vanny Adol, and today I'm really excited. I am interviewing a friend of mine. Her name is Joy. Say hi, Joy.
Hi everyone, YouTube world.
YouTube world. So I met Joy 10 years ago, 2008. Wow, 10 years ago. And doing a research internship at MIT. I was an undergrad and she was a grad student, and she was actually nice to me. She spoke to me. And we kept in touch like 10 years later. So this is she's amazing. I'm really excited to introduce her to you guys. And so tell us a little bit about your background and your academic history.
Cool. So yeah, when I met Vanessa, I was a research assistant at MIT. Before that, I was doing my undergraduate degree at NC State, at North Carolina State University in Raleigh, North Carolina. I'm from North Carolina originally. So I did computer engineering and electrical engineering there. And then I went straight out of undergrad into grad school.
That's when I met you.
Yeah, and I did my master's and my PhD in electrical engineering at MIT.
Okay, yeah. And what do you do now?
Now I'm in a wild and crazy world all the way on the other side. So I always say I'm completely full stack, because we were just talking about some of the process engineering stuff that I did for my PhD. But now I work more on the hardware side doing product development. So I work at Apple, building hardware for Apple as opposed to doing fab stuff.
Yeah, go ahead. So, how do you feel like your background, influences the way you approach your STEM projects?
I think, I guess more my background in terms of the way I was raised. I wasn't really super into Legos. You know how most people say.
I was coding when I was 5.
Right. We didn't have that in North Carolina. They probably do now, I'm sure. But when I was in school, both of my parents were entrepreneurs. They worked together in a construction business. So I saw a lot of just problem solving every single day, but not in a technical sense in terms of trying to code some algorithm or trying to figure out just the right etch process for a specific device, but really thinking through okay, we have a drainage system for this house. Oh, it's an older house. I know they were built this way. They have this type of foundation, and trying to literally, I would see my dad doing his version of a schematic, literally drawing out, and picking problems apart. So I think now I always go pen to paper first, or to a whiteboard first. As soon as we start talking about something or conceptualizing something, I immediately start writing.
But that's great, because every big problem just needs to be broken into little components, and you need to pick the right part to start solving first to do it correctly.
Yeah. So I definitely do that. That is my I'm a construction worker's daughter. And that's the first thing that I do.
It's awesome. Well, it's a good thing you work in hardware now, at the most successful company in the world. Apple, am I saying?
We're trying to figure it out. Look, we're falling behind in a few categories. We're trying to figure it out.
Apple's still doing fine.
but definitely, I think more so on the way in which we were taught at NC State too, was also not very a Socratic or scientific method, which is hard to say for a undergraduate engineering
program. Don't worry, it got you a PhD at MIT, so it's fine. I think it worked.
But I feel like at NC State, it was a bunch of don't start from square one and think you're inventing the wheel. Get online, get on Stack Overflow, go look at schematics, go look at other designs, and figure out what are the problems that have already been solved. So even if it was
work smart, not just hard.
Working smart, looking to see what was out there, looking at all the prior art of that particular area, and really figuring out where the new problems were. So I definitely do those two things first: Google and write. Those two things I do number one.
That's awesome. So how did you decide on grad school, and why?
I think I decided on grad school not the most scientific way. It was more of I felt at the end of undergrad, I didn't know enough. I had tried so many different things that I felt I didn't know how to do one thing well, which I didn't know that I needed to at that point. But it felt like everybody else was yeah, I'm going to go work at this company, or yeah, I'm going to go do this thing. And I was just I don't feel I know enough to have somebody pay me a full salary and health insurance for something that I learned at undergrad,
right?
Which was true, but I felt I needed to learn more. So I knew at least wanted to do a master's.
So there's some personal drive, and you need to learn more. Okay,
but then I did do an undergraduate experience similar to what you did at MIT at Cornell when I was a junior.
Okay,
so going into my senior year, I spent a summer at Cornell University at their what they call CNF, the Cornell Nanoscale facility. And I was this fab stuff is kind of cool. And then when I was talking to my PI at the end of the summer, he was oh, you're getting a PhD. And I was wow, that's for a job. He's no, you need to get a PhD, because otherwise you're going to be doing what somebody else tells you. as opposed to actually building devices and doing things that you think are interesting. So he kind of planted that seed. Professor Tawari definitely like planted that seed of like, you have to do this. Right. And I was like, okay, well, if I get there and the master's doesn't work out and I just, leave with just that, or the PhD doesn't just work out,
just leave with the master's.
I was like, I'll do that. That'll be fun.
I'll just give it a shot. See, this is a common sort of theme with all the PhDs I've talked to. There's always that one professor or PI that says, you need to get a PhD, and you're just like, okay.
I was like,
and also you do a research internship, and then you sort of get influenced to get into grad school. So I guess that's the key, the major key.
Somebody just has to put that little seed in there.
And it grows. So what steps, besides, the research internship, do you think you took that prepared you for grad school, for success in grad school?
That's a good question. I don't know. I guess I'd have to think about that a little bit more, because I feel like I was super late to the game, because this was like literally the summer before my senior year that I was even thinking about going to grad school.
Really? Okay.
So I had to like rush and take the GRE and like do all of these things. So I think it was more so luck on my side, or being blessed on my side, that like I didn't take the process overly seriously. So I didn't like stress out about getting a ton of applications and only apply to a few schools. I really took the process as it came, and I didn't like stress myself out.
That works too.
I definitely also did try
let go and let God works too.
I had to, because at that point I had like 6 months. Like, am I going, am I not? And the other thing is that one of the good piece of advice that I think I probably got from people at MSRP, like just watching like Professor Toll and other people talk about how to apply, was actually using the experience that I did have to talk about it in a way that was like what a researcher would need. So even though I had done a bunch of like working at IBM and Intel and all these places.
So you had done industry internships in undergrad? Okay. So that also prepared you in a way.
Yeah. So I basically talked about them as if they were a research problem. Like, hey, I went to Intel. They wanted to do this like, modeling work on yield. I didn't do any fab work, but I was seeing like die yield information, and we were trying to figure out like
nearest neighbor analysis. For preparation for grad school, especially if you did fab. And fab is fabrication work. The fab is an institution that builds semiconductor devices. So when she's talking about fab, that's what she means.
Yeah. So I essentially used those experiences and talked about them as like, here was a problem statement. These are the things that we tried. Here were our methods. Here were the outcomes, good or bad. Here were the next steps. And literally it's written like a research proposal, right?
So how did you find these opportunities in Intel and IBM? Do you have any advice for people who are in undergrad and trying to find these internships?
Yeah, I mean, I was blessed because I went to a huge state school. Again, I went to NC State. You got 30,000 students. 60% of them, I think, are engineering. So we had these huge career fairs, and literally I just went to the career fair for my first internship. And we had a lot of programs. Like we had this like engineering entrepreneurs program, which kind of like paired students with smaller companies. The Intel thing actually came about from literally going to a career fair, hearing about an opportunity, and when I applied, they said, oh, we have, X amount of jobs that we're looking for students for. So yeah, literally it was going to career fairs and applying through my department. It was nothing like I was out there doing anything fantastic.
So be proactive and go to career fairs and network essentially.
But I do think we have an added advantage of going to these larger engineering schools because companies come there to recruit us. Yeah, so we kind of have the better of the dating side of like they're coming to find
they want you.
They want us.
So it's easier that way. Yeah. That's awesome. Are there any steps you wish you took, or do you think you were well prepared?
I think I would, if I would have done any more, I might not have gone to graduate school because I might have been a little too scared of it, know? Right. So I think I had just enough of a taste to have interest, but not be too daunted by like all these crazy.
Like if you had worked in a lab for 2 years and seen a grad student crying, you're like, okay, no, I don't want that life.
Yeah, I would have seen the both extremes, and I saw just enough.
Just enough that you're like, okay, I'll try this.
Yeah, just enough to not scare me away.
That's awesome. Okay, so we're going to get to the part where I'm going to ask you to give me a little synopsis of your PhD. So tell us what you did.
Yeah, so when I came into graduate school, I knew I wanted to do things around nanofabrication. That just means being able to actually build smaller devices. And those devices could be anything from like the chips that go inside of phones and TVs and all different types of electronics that are getting miniaturized.
Smaller and smaller.
Yeah.
So that's just a huge industry.
Yeah, but I also thought two things I thought were really cool was one, being able to build something from like literally nothing to an actual device that I could test and see how it behaved. But also looking at different types of like exotic materials. Because at that time when I was going into graduate school, everybody was talking about all these different types of like, they would
3-5 semiconductors.
Yeah, they would talk about gallium nitride, talk about all these different 3-5 semiconductors that were like nanomaterials. They had this new buzzword. And a lot of people were thinking about using them for like bio-related or medical-related devices. So when I went to graduate school, I knew I was interested in fabrication, but I wasn't really sure what I wanted to do. And so what I ended up doing was working on novel processes. So there's tons of processes that these fabs and fab houses use to build devices. And one of the processes is called planarization. And we talked a little bit about this before, but it's essentially just making things flat, making things planar. And the cool thing about this process is that it's really expensive. So lots of people care about it. It's one of the processes that is actually
cutting back costs is the huge in every industry, of course. So
cutting costs, but it's also a technology enabler. We always talk about miniaturization, making things smaller, making devices like have the smallest line, which you'll hear things like Moore's Law and all these things. All the concepts means that we're driving down the cost at the same time we're driving down the size. So this was one of the key processes in actually enabling that. And my professor, he had a lot of ideas around like, let's step away from what we do traditionally and figure out how can we model new ways of doing this. So one of the things that we did was we looked at the process of chemical and mechanical planarization using different chemistries like electrolytes and nanoparticles that are inside of those electrolytes or suspended inside of those electrolytes, as well as big scale or large scale mechanics, basically using pads, things like you would use in grinding processes in metals,
like just
in glass.
Grind it flat.
Grind it and make it flat. Just think about cooking. I always think about cooking examples where you're like, you see people like on these cake baking shows where they're like using really small knives to make the surface really flat so that they can ice that cake and make it just perfectly flat and look beautiful.
Or if then it would be chemical if they use a fire to flambe, right?
Sometimes they use fire. So what we did was we took a process that used both chemical and mechanical components. And what we did was we built these kind of like semi-physical models where we said, well, what if we just get rid of the mechanical component altogether? We take this huge pad that we would use to make things planar and then just use that same material in a nanoparticle form, literally really, really tiny particles that were cheaper. We were using less of the product. They could be affluented
cutting costs there.
You're cutting costs. You're making it a little bit more environmentally benign by allowing those to then dissolve in the electrolyte after you're done. So we're doing things for the environment. But we said, okay, well, let's model those things. So we built a lot of theoretical models to show how we would actually get the same amount of planarization or level of uniformity on a device or on a wafer, which is what people cut up and make it to chips.
And this is important because every chip you have starts out as a layer of a bunch of flat layers, essentially. And then, other engineers come in and design the architecture to make your chip actually do what you want it to do. But it is very essential at that level to deposit very flat sort of layers, essentially. So you have a defect-free devices.
So we did a bunch of theoretical modeling, so folks didn't have to get in bunny suits and do tons of experiments.
Oh, you did the bunny suits too?
I did also do the bunny suit as well. So we built these great models that were both semi-physical and empirical. So we did do experimentation. We looked at both the chemistry around the particle surfaces. So a lot of my PhD thesis is about just that surface chemistry and how it reacted in different environments and how it attached to things, whether it was the device we were trying to build or the other particles in that same mixture. And then we did the experiments to prove that this could actually work. And then we shipped them off to Intel and they paid for the PhD and I got out of there.
Awesome. So you actually worked with industry in collaboration.
Because they were really interested in, like you said, the cost savings. They always are looking at
So did you improve the throughput as well? Or the yield or throughput, or just cut back costs and match?
Just cut costs. So it'd be great if we could,
So that would be the future work. Throughput. Some other PhDs work.
Yeah. Some other PhD work to say, can we scale this? So we proved that we could do it. It could be done with metals and dielectrics, which are just really thin films that are from silicon itself, which is what the base material is. But we never proved scale, right? We proved theoretically I can model it for you. We can control the process.
What did you use for your modeling?
We didn't scale it. So we did everything in C because then we take that C code.
Okay, so now guys, we've done Python, MATLAB, now it's C. So aspiring engineers just keep learning.
Love MATLAB though, because MATLAB is great to visualize. So one thing I did use MATLAB a ton for in my PhD is to visualize. When you think about a wafer or a die, which is just a single chip, visualizing it is so important because we want to see, like, what does the design look like before I hand it off to another engineer to do their etching or to do their design. So we did use MATLAB a lot to visualize what the surface looked like at a certain point in time. But we use C a lot because then it can be turned into machine code that they can actually run in the fab to do those scale and global experiments. So
Python would be good for that too, right?
Yeah, but at the time, when I was in grad school, even though it wasn't that long ago, Python wasn't very popular as a scripting language because people thought of it as like it was such a large jump to actually get into machine code when it's not, but we can talk about that another time. But a lot of people did not see Python as a viable path to go from theoretical and like proving out models to actually getting to machine code that you could run every day. Yeah.
But now that's all people use.
Now people love using Python.
Yeah.
All the rage. And the funny part about it was that when I was TAing while I was in grad school writing C, I was teaching undergrads Python because that's when MIT decided that they wanted to do entry-level computer science or CS students learn Python as their first language. So, I was living in both worlds and trying to figure out what made sense. So.
Do you use any of that modeling in your current job?
I don't in my current job. In my current job, that low level of modeling, because literally we were getting down to particle scale, chemistry, looking at electrons and how they were behaving with different types of chemistry compositions. Now I'm way higher up in the stack, as you would say. And so the modeling that we do is more physical. Like we really don't do any like low level modeling.
I guess that's common in industry, right? You sort of leave the very fundamental problems to graduate school and research institutions.
Yeah, and we work a lot with universities. Contrary to popular belief, Apple has a ton of university relationships. So there are a ton of people who are doing
you worked with Intel in your PhD. All right. So tell us, what was the most rewarding part of your PhD?
Most rewarding part of my PhD, I don't know. I really like learning new stuff. I get really bored really fast. I mean, it was all rewarding to me.
Even in industry, you don't get bored?
No, because there's always something going on. I feel like in industry, especially in Silicon Valley, there's always something new going on. So we don't really have the like monotony problem at work. Whereas in grad school, sometimes you can have that because you're looking at the same problem every day, all day. But I think the most rewarding part is just like getting results, like actually seeing the results. Like sometimes
and shipping it off to Intel must have been great because it was actually applicable work stuff you were working on.
It was applicable work. The hope is always like that they'll actually use that work.
Right.
But I think the most rewarding part was actually just getting results. I think you spend like a week or 2 weeks on one wafer and you're just like, please God, don't let me drop it.
I know.
Please God,
that's the thing with these chips in your phone. You don't realize how fragile they are. And that's why you have to wear the bunny suit because you're basically protecting the chips from you. It's insane. So
I think
a lot goes into
as soon as you look at that SEM image, you're just like, this is just a scanning electron microscope image. Like when you see that image and it actually looks like what you want it to look like that's very rewarding. Yeah. So I think that was probably the most rewarding. And then just meeting other grad students, helping one another. Like
talking to undergrads and getting friends. Thank you so much for that. Because I've been a grad student and you understand, grad students usually consider undergrads very annoying. So it's rare for a grad student to actually be friends with an undergrad. So
I love undergrads. I love teaching. I lived in the undergrad dorm for a couple years during my PhD, just helping. That's always fun. It's always fun interacting with students.
So as you've grown in your career and matured, personally, what have you realized about yourself that you feel like you needed to work extra hard at and you're working on getting better at right now in your career?
I think it's just complacency. Like it can get so easy to just do the same thing over and over again because you're good at it, like that one thing. But I think one thing I've learned about myself is that I have to challenge myself. I have to continually challenge myself because I see a lot of people, especially now going from like graduate school to startup to industry, that a lot of people just rest and best, as they say. Like they just
coast at work.
And it's so easy to do
so
that.
It's so boring.
So one of the things I've learned about myself is that I have to push myself daily. I have to read. Even though I'm an avid reader, sometimes if I feel like it's for work or if I feel like it's mandatory, I don't want to do it.
Yeah.
So I have to push myself to continually read papers, continually read the blogs. Like the tech blogs are really great. I know people say like blogs are bad, but I learned so much about how you just interact.
Stay on top of your industry, basically.
Stay ahead of it. Stay ahead of it. Always be reading. Always be doing those things that in grad school you hated to do. Doing lit reviews and stuff like that. It's so vital and necessary to do your job well that way. So
that is great advice. I need to do more of that. I'll get some
so
tech blogs from you.
It's so hard.
It is really hard.
But yeah, that's definitely something I have to push myself to do.
Okay. So do you have any advice that you were given to your younger self right now? As you're looking back 10 years since you started grad school?
Advice to my younger self. I don't know. I think I always think about these things like, would I have done something differently? Or like, why did I not do X, Y, or Z? But I don't know. I think I just would have kept reiterating to myself to just finish. Because I think that motivating factor to
just
do things well I think it's just like something that we all need to hear all the time. And I'm sure I was telling myself that then, but I would just keep telling myself that, because as time passes, you see how those things kind of have compounded effects, you know? Of like, sometimes you just want to kind of like, oh, get some minor, like I did like Kimmy for my minor, like just want to get some minor over and done with. It's like, no, do it well. You never know when those things are going to come back, you know, and those skills are going to be useful to you. So,
and it's usually the little things that sort of matter. I put some things on my resume and like got into an interview and they're like focused on that. And if I just sort of put that on there and I didn't, you know, pay attention, I would have lost that job opportunity. Everything matters.
We were just talking about my friend who was applying for jobs, and he was like, oh man, yeah, I was thinking about including that. And then I asked him a couple questions about it. He was like, oh man, I got to brush up on that. Like, you have to keep pushing yourself, you know, and it's going to be worth it. And it's going to be a thing that you're going to use either to help other people or to help you in your job. Because sometimes I find that like tons of brilliant people I work with, awesome people, but there are things they don't know, the things that I do know, but I have to keep my mind refreshed on those concepts, refreshed on those things, on those ideas as they come up. I want to be able to speak to them and bring value at work. So
keep learning. I guess that's a good
keep learning all the way.
Like, keep learning all the way.
Don't dabble. Just go in. Just do everything you need to do.
All right, that's a good way to close this. So thank you guys for watching. So keep learning, focus, learn C, MATLAB, Python, and read the tech blogs and stay on top of what everybody else is doing. All right, thanks again. Sorry, that was weird. Thanks again for watching. My name is Vanessa, and this is Vani et al. And click the link below to learn more about Joy's PhD work. Bye, guys. All right, thank you.
I thought you were done. I was like, cool, we're done.